Good afternoon. We are going to look at current source inverter fed induction motor drive in today's lecture class. As I mentioned in the last class, we said that we are yet to look at 4 topics pertaining to induction motor. The first one being current source inverter fed induction motor drive. And we will talk about performance of the induction motor when it is fed by a non-sinusoidal supply voltage or supply current. Then we would migrate to field-oriented control of induction motor drive, and after that we will look at direct torque control. So let us try to look at now current source inverter fed induction motor drive. That's what we are going to look at now. So what is the major difference between a current source and voltage source? If you look at an induction motor which is fed by a voltage source, so normally from a 3-phase supply, what we get in India, that is 3-phase 400 volts or 440 volts, 50 hertz. This is what we are supplying. So the voltage is already set in stone. Whereas if we are looking at the current drawn by the induction motor, let us try to look at the equivalent circuit of the induction motor. This is the per phase voltage, which is V1. And we have R1 and X1, which are the leakage reactance and resistance of the stator side. Again, per phase values. Then we are going to have XM, which is the magnetizing reactance. I'm not including the core loss component here in the equivalent circuit. And this is R2 dash divided by S, which is the rotor resistance reflected on the stator side, and it is divided by S to indicate how much is the mechanical power developed along with the rotor copper losses. Then we are going to have X2 dash, which is the leakage reactance of the rotor circuit with respect to the stator side frequency. So this is the equivalent circuit of the induction motor. So when we are talking about starting of the induction motor, we are going to have S equal to 1 during starting. So because of which, if you look at the rotor circuit is really going to have a very, very small amount of resistance and small leakage reactance. So the impedance offered by the rotor circuit, which is R2 dash plus JX2 dash, which is the rotor side reactance Z2 dash, this will be low. Because this is really low, the current taken by the rotor circuit, if I may call this as I2 dash during starting, that is going to be really, really large. And the magnetizing current may not be that large, but because of the rotor current being large, you see that normally voltage fed induction motor drives take a huge amount of starting current. That's why we say that generally the starting current of the induction motor is anywhere between 6 to 8 times that of full load current, right? But if I am feeding it with a current source, the current source magnitude is going to be fixed. It can be 1 per unit or something like that. So let us say the current source magnitude is 1 per unit. So if I am feeding this with 1 per unit current, and if I say that XM is going to be maybe 10 times or even 15 times that of Z2 dash. So if I'm going to have 15 times that of Z2 dash is going to be XM, in that case, XM is going to be the current flowing through XM, which is IM, that is going to be really, really low. So IM will be low, whereas I2 dash will be large. But what we mean by large or low is also relative values of them, each other. So if I'm totally supplying only 1 per unit, I'm going to have 1 by 16th per unit or 16th of 1 per unit, that is going to be Im, whereas 15 by 16th per unit is going to be I2 dash. So the magnetizing current being low will cause the flux to be really, really low. So CSI fed drive, we are going to have the magnetizing current to be low during starting. So if that is low during starting, very clearly flux is going to be low. If flux is low, then correspondingly the torque capability of the machine is going to be low. So we are not going to get a good starting performance for a CSI fed motor drive very clearly if I am limiting the total current that is being supplied to the motor. Whereas here in the voltage fed case, we are not limiting the current drawn by the motor. It can be 6 to 8 times the full load current. Whereas when I talk about a CSI fed drive, the current is limited to 1 per unit or 1.5 per unit, because of which I'm not going to be able to see a good amount of torque being produced during starting. So the starting torque or starting performance of the CSI fed motor drive is not going to be as good as voltage fed induction motor drive. That is for sure. Now let us look at different operating conditions of the CSI fed drive. So under no load condition, if I analyze how the induction motor drive is going to perform when it is fed with the current source inverter. So again, let me draw this equivalent circuit of the induction motor, assuming that this IS is going to be 1 per unit, for example, and I'm going to have R1 and X1, and I'm going to have this as XM, and this is going to be R2 dash divided by S, and then this is going to be X2 dash. So this is going to be the the kind of equivalent circuit we consider always. So if I am looking at what is the kind of current that is flowing through I2 dash, that is the rotor circuit, and what is the kind of current that is flowing in the form of magnetizing current, I should be able to write the expression somewhat like this. Im should be equal to whatever is the current that is flowing through the entire stator winding of the motor multiplied by, now these two are parallel to each other, that is XM and R2 dash by S plus JX2 dash, they are parallel to each other. So I should be able to write this in the form of current division rule. So I should be able to write that Im square equal to Is square multiplied by the other impedance, which is R2 dash divided by S, the whole square, plus X2 dash square divided by the total impedance of the total two parallel paths, that is R2 dash by S whole square plus X2 dash plus XM the whole square. So this is the current what we get in terms of the current division rule. The same way I should be able to write I2 dash square will be equal to Is square multiplied by Xm square, because that is the impedance of the other path, divided by R2 dash divided by S, the whole square, plus X2 dash plus Xm, the whole square. So these are the expressions that we had written earlier also when we were talking about the previous topic, where we had actually derived the expression for DC dynamic braking condition, and we had specifically used these expressions ultimately to derive the slip and the torque and everything. So the same thing I'm writing again for current source inverter fed induction motor drive case as well. So from comparing these two equations, and one more thing we can write is if I am talking about this particular voltage which is appearing across this Xm as E, again I should be able to write E square equal to Im square multiplied by Xm square. And the same way from if I call this as equation 1 and if I call this as equation 2, so equation 2 can be written as this is equation 3. So equation 3 can be written as is square multiplied by xm square is equal to. Then I can write I2 dash square multiplied by R2 dash divided by S the whole square plus X2 dash plus XM the whole square. Okay. So from these two, we should be able to get what is the slip value. We should be able to get what is the I2 dash value and so on. All those things we should be able to obtain from these two equations. If I may call this equation as equation number 3 again. So we should be able to obtain all those things. But qualitatively speaking, we can very clearly say that under no load condition, slip is going to be approximately equal to 0. This is the case with no load condition. So when you are having a voltage fed induction motor drive, because this rotor current literally becomes 0, because slip is 0, this impedance, rotor impedance will be infinity. This will be close to infinity. Because of which the rotor current is going to become extremely small. If the rotor current is small, then the magnetizing current drawn only will be the current totally drawn from the stator side in the voltage fed case. Whereas in current fed case, no matter what I am pumping in 1 per unit of current, whether the motor is under no load condition or loaded condition, the current source does not care. It is going to supply 1 per unit of current. So if it is supplying 1 per unit of current under such a condition, then we are going to have a big problem in terms of that entire current flowing through the magnetizing branch, and that is going to cause saturation. So 1 per unit current flows through Xn, that completely flows through Xn, because of which we are going to have saturation occurring in the motor drive. So saturation occurs in the magnetic circuit. So if the saturation is happening in the magnetic circuit of the induction motor, then what happens is the induced EMF could be large. You could have a large flux basically established in the air gap. So the speed could be higher than the nominal no load speed of this induction motor drive. And if you load the induction motor even slowly, the fall in the speed is going to be somewhat smaller than the voltage fed case. So if I try to plot the voltage fed induction motor drive and current fed induction motor drive characteristics along this, let us say this is omega m, whereas this is going to be TE. And if I am talking about voltage fed case somewhat like this is what is the voltage fed case. Now, the current fed case will be in such a way that I am going to have the droop much lower than what you might anticipate in the case of a current fed motor drive. So this is going to be current fed case. And here, if you look at it, the starting torque is going to be really, really small. That's what we had talked about. Whereas in voltage fed case, we are going to have a good amount of starting torque. So the voltage fed case will have this as the starting torque. Whereas the current fed case will have only very, very small amount of starting torque. Now, you can see that under no load condition, if I call this as omega S, under no load condition, we are going to have the starting point to be the same, but as you start loading the induction motor, the voltage fed case has larger droop. You can see that it has fallen quite a bit. Whereas in current fed case, the fall will be really, really small as compared to voltage fed case. So, if I am talking about, let us say, I'm loading the induction motor in current fed case as well as voltage fed case, and I'm talking about 1 per unit of current being pumped through the induction motor. So if I try to do that, and if I look at rated torque, at rated torque condition, what is the kind of operating point I'm going to have in the current fed case? I can have either point A, this is point A, or I can have the operating point as point B. So I could have either of the two operating points, either A or B as the operating point. So if I examine what is the operating point A, it is going to have a higher speed and it will have a higher flux. Because higher speed means slip is going to be smaller. So slip is smaller. So if slip is smaller, then the impedance of the rotor side is higher. So the magnetizing current drawn will be higher. So there will be higher flux. So magnetic circuit will saturate. So magnetic circuit could saturate. And the rotor current will be smaller. So if rotor current is lower, but the magnetic circuit saturates, we will have basically core losses to be higher. And copper losses are going to be, especially rotor copper losses are smaller. So this is the case with respect to point A, what is shown as the operating point here. So that is point A. Whereas if I look at point B, this point B will be having lower speed. So exactly it will be opposite of whatever we said in the case of point A. So this will be lower speed. So if I have a lower speed, so this is going to be having lower speed. Let me draw this once again. This axis is gone. So this is lower speed. And we are going to have higher flux, higher slip. So that means rotor current will be larger. Magnetizing current will be smaller. So which means no saturation. So we are going to have rotor copper losses will be higher. But if you look at the characteristics, you can see that B is coinciding with voltage fed characteristics, whereas A is above the voltage fed characteristics. So out of these 2 points, if we are looking at which one is more advantageous, we would not generally go with saturation of magnetic circuit because you might overload the machine magnetically, which is actually not a very good idea. And another thing is core losses are going to be higher, means again, we may be playing around with the magnetic design of the motor, and we may actually cause a havoc in terms of the functioning of the motor itself. So generally point B is preferred as compared to point A. So point A is generally not preferred, rather point B is preferred because it also coincides with the voltage fed kind of characteristics. So invariably, current source inverter fed induction motor drives are operated with respect to, if you look at the characteristics of the torque speed characteristics of the machine, it's operated only in unstable region. Point B actually resides in the portion which is corresponding to steady state unstable region, whereas point A is in the stable region. So invariably, an unstable system can be made into a stable system by proper compensator design in a control system criteria. So, current source inverter fed drives are invariably operated in open loop unstable portion. So, they have to be generally operated as closed loop controlled drives. So without closed loop, so closed loop control design is essential for a CSI fed drive because it is generally going to operate in the unstable portion of the steady state speed torque characteristics. That is the reason why invariably we are going to operate CSI fed drive only with the closed loop control. We'll hardly ever work on open loop control of CSI fed drive. We have spoken only about the CSI fed drive right now only with the particular frequency which is corresponding to omega S. So let us try to look at variable frequency operation of a CSI fed induction. So we are looking at variable frequency operation of a CSI fed induction motor drive. So what we are looking at is the IS, what we are feeding here is going to be variable frequency. So how we are generating that variable frequency current, that is a matter of detail, which we will address within a short while. This is going to be R1, X1 on the stator side. This is going to be the magnetizing reactance XM. And this is the rotor reactance as seen, rotor resistance as seen from the stator side, which also takes care of the mechanical power developed. And this is X2 dash, which is the rotor side leakage reactance as visualized from the stator side. So this is the equivalent circuit of the induction motor. Now we wrote the expression for Im. I'm going to write that again. So I can say Im square, which is the current that is flowing through this magnetizing branch, the square of that. So Im square is going to be the other side impedance, that is R2 dash by S the whole square plus X2 dash square divided by the total impedance of the two parallel paths, that is R2 dash by S the whole square plus X2 dash plus XM the whole square. This has to be multiplied by IS square. So this will give us what is the magnetizing current. Okay. The same way we should be able to write I2 dash square will be equal to, this is going to be XM square divided by R2 dash divided by S the whole square plus X2 dash plus XM the whole square. This has to be multiplied by IS square. This will give us what is I2 dash square, and we should be able to write the torque. So electromagnetic torque is going to be 3I2 dash square R2 dash divided by S. multiplied by omega s, where omega s is the synchronous speed, which is decided by the frequency at which this IS is being generated. The source current is being generated. So this is the electromagnetic torque. Now we are assuming that this is going to be of variable frequency. So if I have, let us say, A, which is the current, the present frequency divided by the rated frequency. So this is the ratio of the present frequency to the rated frequency. So if I have this as A, then I should be able to write Im. So I can say Im square equal to, the resistance probably would vary somewhat slightly because of the frequency variation, but we are neglecting it. It can change due to skin effect, but I am neglecting it here. So I can write this as R2 dash divided by S, the whole square, plus A square X2 dash square. So this is the variation in the reactance because of the difference or variation in the frequency as far as the applied current is concerned. The same thing will hold good here. So this is going to be R2 dash by S the whole square multiplied by X2 dash plus XM the whole square multiplied by A square. So if I try to bring this, and I can write this as IS square, of course. Now, if I am dividing the denominator as well as numerator by A square, in that case, I can write this as R2 dash divided by AS the whole square plus X2 dash square divided by, again, I can write R2 dash divided by AS the whole square plus X2 dash plus XM the whole square. This has to be multiplied by IS square and that will be equal to Im square. Now, if I want to keep the magnetizing current at a constant value, I don't want to change the magnetizing current because I'm talking about constant flux operation. In that case, if I am keeping IS square at 1 per unit or whatever constant value, then as long as I keep AS as a constant, magnetizing current as a constant. So just to put it very clearly, as long as AS is a constant, irrespective of variation in the frequency, irrespective of variation in the frequency, we will be maintaining Im as a constant, that is the flux as a constant for a given value of Is. So for a given value of Is, whatever be the frequency of this Is, we will be maintaining constant flux operation as long as AS is maintained as a constant. About this AS we spoke when we were talking about VSI fed induction motor drive. So A times slip, I can write this as A times slip can be defined as A times omega S minus omega M, whatever is the mechanical speed of the induction motor's rotor, divided by A times omega S. Because A times omega S is now the synchronous speed, omega S being the rated synchronous speed. So we will be able to cancel this and this now. So this, from here, I should be able to write this as A S omega S is equal to A times omega S minus omega M. And A times omega s is synchronous speed, omega m is the rotor speed. So this is actually slip speed. So when we say AS is maintained as a constant, that essentially implies that I'm going to maintain slip speed as a constant. So if I'm keeping slip speed as a constant, whether it is current source fed induction motor drive or voltage source fed induction motor drive, it doesn't matter. It is going to hold the flux as a constant. That's what it implies. So if I want to keep the magnetizing current as a constant, I should show it as though when I am talking about a slip speed of 0, if the slip speed is 0, at that point, I will not have any rotor current. There will not be any rotor current at all. So whatever is the current source value, that should be equal to the magnetizing current required for establishing rated flux in the air gap. And once I am going to load the induction motor, the machine will be drawing more and more rotor current. So the rotor current I2 dash plus IM, both of them put together will make up for IS, which is the source current. So I should be able to increase the source current when I load the induction motor further and further. So this is the variation of IS with respect to slip speed. So as the slip speed increases, you should be increasing the source current further and further. And when the slip speed is 0, the rotor current is going to be 0. So we will have the total source current equal to magnetizing current. The same thing holds good for negative slip speed as well. So we will have a characteristics for the current source value somewhat like this. The current source value will be equal to the magnetizing current when we are talking about 0 slip speed. And as the slip speed increases, because the rotor current value increases, we will have the total current increasing slowly, and it will be increasing as per the torque requirement of the load further and further. So in general, if we are looking at current source inverter fed induction motor drive functioning with variable frequency control, we will have at no load condition, the current source value should be only equal to the magnetizing current. And as long as we are wanting a particular value of load torque, the slip speed should be maintained as a constant. The flux should be maintained as a constant. Only the frequency of the current source inverter has to be varied. The DC link current need not be varied. The DC link current can remain as a constant depending upon how much is the torque requirement for the load that is involved in the current source inverter fed induction motor drive case. Okay, so so in that sense, CSI fed induction motor drive and VSI fed induction motor drive both function very, very similarly. Only slip speed really decides what is the kind of current magnitude that needs to be injected as per the load requirement, load torque requirement. But if we are talking about a constant load torque, we are really going to keep the slip speed as a constant, the magnetizing current as a constant, the current source value as a constant. Only thing we may be varying is frequency as per the speed requirement of the motor load. Okay, so let us now try to look at the operation of the CSI fed drive until rated speed and above rated speed. So if we are talking about until rated speed, if we are talking about the rated torque condition. Clearly, the slip speed will also be rated slip speed. So the current value would have reached, if let us say this is the rated slip speed, then we would have, as far as the current source inverter is concerned, we would have reached the rated value of IS. So this will be rated IS. So we cannot really allow the motor to go beyond rated IS, and at rated IS and at rated frequency or rated speed, the machine would also have reached rated value of voltage, because if you look at the overall voltage, the input voltage is going to be equal to whatever is the input impedance of the induction motor multiplied by the current that is being pumped in. This is R in plus Jx I in multiplied by Jx, the current that is being pumped into the induction motor. So as per the equivalent circuit of the induction motor, we should write this as R1 plus Jx1 plus Jxm in parallel with R2 dash divided by S plus Jx2 dash. This is the total impedance of the induction motor. And this has to be multiplied by I in ultimately to get what is the total voltage. And if we are talking about rated speed and rated load condition, very clearly this input voltage would have reached whatever is V1 rated if we are talking about I in being rated IS value. And we are also talking about rated speed condition, rated speed and rated torque condition. So if we want to go beyond rated speed, so until rated speed, we should be able to increase the frequency. There is no problem. So until we reach the rated frequency, the current that is pumped in also can be 1 per unit or rated current. So the machine will be able to fend for rated value of torque as far as the load demand is concerned. But once you want to go beyond rated speed, if we try to still pump 1 per unit of current with rated flux and rated value of rotor current, in that case, we, in all probability, we would have had increase in X1 for a higher frequency. We'll also have an increase in X2 dash as well as Xm for a higher frequency. So this voltage would have gone beyond rated value of voltage, and which is not good for the insulation of the stator windings. So that is the reason why if we want to operate a CSI fed drive beyond rated speed, somehow we have to find a way to limit the voltage. It should not go beyond the rated value of voltage. So it's very, very difficult to monitor the voltage on a continuous basis in a CSI fed drive. That's the reason why normally CSI fed drives, we don't operate it beyond rated speed. If at all we want to operate it beyond rated speed, it should actually kind of cap the voltage to rated value. And if it is capping the voltage to rated value, it is as good as a VSI fed drive. So this will function similar to a VSI fed drive. It's not going to be any different from a VSI fed drive. So generally CSI fed drives are operated at lower speeds, and they are generally operated for obtaining variable speed from 0 speed to rated speed condition. And how is a CSI FET drive implemented? So let me try to give you a little bit of introduction to how a CSI FET drive is implemented. So if you look at the CSI FET drive normally, we are going to have probably a current source. The current source is generally a DC voltage source with a very, very large inductance. So the current is going to be maintained somewhat constant because of this large inductance. This LD is going to be a large inductance. So this is going to maintain a very constant or, absolutely oscillation-free current. So we may have a current through, say, A phase for 120 degrees like this. Then there will be a 60-degree dead band and then another 120-degree current in the negative side. So this is probably going to repeat itself as far as the A phase is concerned. So we can say this is 0 degree, this is 120 degree, this is 180. Then this is 180 plus 120, which is 300. And we are going to have this as 360 degrees. So this is IA. So this is going to be A phase current. So we can similarly draw B phase current and C phase current. So if I draw B phase current, I should show it as though it is starting from this 120-degree region. So this is going to come up like this. And this will spread itself for 120 degrees. So this is 60 degree and this is another 60 degree. So this is going to be B phase current. And for the next 60 degrees, this is going to be at 0 value. Then it will again increase from here and go like this. And the same way, this will have a waveform somewhat like this. So this is going to be IB. So similarly, I should be able to draw IC as well. And we can definitely look at this waveform in terms of harmonic analysis or Fourier expansion. Very clearly, this current being a quasi-square wave current will have a lot of harmonics. So this is definitely going to have fifth harmonic, seventh harmonic, and so on and so forth. And the RMS value will be very similar to what we derived in the case of rectifier. So if I call this as ID, so we are going to have root of 2 by 3 times ID as the RMS value of current corresponding to A phase, B phase, and C phase respectively. Now, we are looking at this current flowing through the three-phase induction motor. So the three-phase induction motor is going to have its windings like this. And let me show this as the inverter. Please note I'm showing a thyristor inverter here. I'll get back to you as to why we are using a thyristor in this particular case. Now this is A phase. Now this is going to be B phase, and the C phase current will also be coming out of here. So this is A phase, B phase, and C phase respectively. Now this A phase, B phase, and C phase, each of them will have leakage reactances. So when the current is abruptly rising or abruptly falling, like what I have shown, that is definitely going to cause an L di by dt visualized at these points, because we are not allowing this current to continue in A phase or B phase or C phase beyond this point. For example, A phase current flows from 0 to 120 degrees. At 120 degrees, abruptly the current has to come down to 0. So whenever the current is abruptly coming down to 0, di by dt is large, because of which the L di by dt manifested at the terminal of A phase is going to be pretty large. So if I draw the voltage waveform corresponding to A phase, B phase, and C phase respectively, let me try to draw that. So if I first draw what is VAN with respect to neutral, if I try to look at what is the kind of voltage that is visualized at this point, this is VAN. Here the current is increasing, so I may have a positive di by dt, and then I'm going to have probably here this is coming down. And one more thing, because it is an inductive circuit, the current should be lagging behind the voltage. So if the current zero crossing is somewhere here for A phase, the voltage might have, the zero crossing might have come right here. So from here, we are going to have a negative voltage. Then it would have again gone further, and you can see this is a negative current. So I'm going to have one more voltage coming like voltage spike coming like this. And here is the current which is going towards positive. From negative side, it is going towards zero. So di by dt is actually positive. So I'm going to have something like this. So this is the kind of waveform we are going to have for VAN. So VAN waveform is somewhat like this. So these spikes can affect these devices adversely. What are sitting in the inverter, those devices can be affected adversely because of the voltages that are appearing, at the terminals of the induction motor. To nullify the effect of this, normally what you can do is, along with the motor drive, if this is the inverter that we are talking about, current source inverter we are talking about, that is supplying the AC current to the motor drive. So these are the three terminals of, or three windings of the motor drive, which is star connected. Now we should be in a position to connect capacitor so that the capacitors will be offering alternate path for the current. Although the motor is not going to carry the current, the motor windings current can be diverted into the capacitor to charge the capacitor. So this inverter will not allow the flow of current, but between the capacitor and the motor windings, there could be exchange of energy. So the motor winding current need not be stopped abruptly like this. Whatever we are seeing here, that need not happen. So there will be an alternate path provided by the capacitor for the current to flow. So these spikes, whatever we see, these can be eliminated completely. So in a VSI fed drive, the leakage reactance of the induction motor is useful to smoothen the current. Whereas in a current source fed drive, the leakage reactance is a big problem. It is actually, a bane, whereas the leakage reactance is a boon in the case of a VSI fed drive. In VSI fed drive, the leakage reactance basically filters the current and makes it more smooth and sinusoidal. Whereas in the case of a CSI fed drive, the leakage reactance creates lots of voltage notches and spikes. So those are going to cause havoc in inverter devices. The inverter devices can completely be blowing. So to nullify those effects, we might have to include capacitors like this so that overall power factor of the induction motor also improves. And we are going to ensure that alternate path is provided for the current to flow, the phase current to flow, so that abrupt changes in phase currents are not visible. Rather than doing this, can we integrate this capacitor into the inverter circuit itself? And that takes us to auto sequentially commutated current source inverter. So auto sequentially commutated current source inverter is very commonly used as an inverter circuit whenever we are talking about a CSI fed drive. So the auto sequentially commutated current source inverter circuit is somewhat like this. Let me draw the circuit clearly. So we are going to have one thyristor like this, and we are going to have one diode and one more diode which will come up here and one more thyristor. So this consists of one leg. So let me call this as T1. Let me call this as T4. This is D1 and this is D4. The same way, I should be able to draw this for the next phase. So this is T3, this is D3, and this is going to be D6, and this will be T6. And the third phase, which is corresponding to C phase, this is T5, this is D5, and this is D2, and this is T2. So this is the complete circuit for the auto sequentially commutated current source inverter. And we are going to have a current flowing through this. So for which we may have a large inductance. And along with that, we may have a DC voltage source here. The DC voltage source could be realized by having a rectifier and an AC source. That's perfectly fine. Now this is going to be the source current which is flowing through this. Okay. Now this is Vs, which is the DC voltage source. Now on the other side, we are going to have the induction motor. So this is A phase of the induction motor. This is the B phase of the induction motor. And this is C phase of the induction motor. So let me call this as A, this is B, and this is C. And we are going to have the three phases here. This is A, this is B, and this is C. Okay, and this is the neutral of the induction motor. Now, the capacitors can be advantageously used here for commutating the outgoing thyristor. So let us say this is C1. Maybe this is charged with plus here and minus here. And this is going to be C3. So let me call this as C3. And let me call this as C5. And the voltage, when I add all the three capacitor voltages, it should sum up to 0. Maybe C5 is with plus here and minus here. And C1 is with plus here and minus here. So C3 can be with 0 voltage. So overall, the voltage across all the three capacitors which are forming a loop, that should be equal to 0 by Kirchhoff's voltage law. The same way, I can call this capacitor as C4. And let me call this capacitor as C6. And let me call the third capacitor, which are all the three capacitors are delta connected, as you can see. So this is going to be C2. Now let us say, let's try to look at how this particular circuit works. So initially T1 and T2 are on. So I'm saying that initially T1 and T2 are on. So we are going to have the current flowing somewhat like this. So let me show that the current flows through T1 and it will flow through D1 and D4, not D4, sorry. It will flow through the A phase. So this is A phase winding. And it is going to return through, if T2 is conducting, this is ZC. So it will flow through this and ZC, and it will flow through D2 and T2, and then it should return to the negative of the source side. So from the positive, it will start and it will flow like this. So the path for the current, let me write, if I may call this as LD. So it will go from VS positive to LD, and it will go to T1, then it will go to D1, and from D1 it is going to ZA, and from ZA it is going to ZC, from ZC it is going to D2, from D2 it will go to T2, and then VS negative. So this is the way the current is going to flow. Okay. Now, when I want to commutate T1 and want to fire T3. So when T3 is fired at the end of 120 degrees. So if you may look at the waveform, what we drew in the previous slide. So we said that from 0 degree to 120 degree, we are going to see A phase carrying the current. So at the end of 120 degrees, A phase device goes off and B phase device is turned on. So that's what we mean by at the end of 120 degrees, we are trying to fire T3. So when we are firing T3, what happens is, let's say the capacitor is pre-charged like this. This is plus and this is minus. Because this is plus and this is minus, immediately as soon as T3 is fired, we are going to have this plus trying to discharge the current into T1 in the opposite direction. So T1 is turned off immediately. So the T1 device is going to be turned off immediately. So we call this as hard commutation, because the capacitor, if you look at it, if this is T1, the capacitor is going to have plus here and minus here, and T3 is turned on, so it is going to work as a short circuit. So we are going to see that a current flows through the capacitor to T1 in the opposite sense. So immediately it is going to be quenched. This device is going to be turned off immediately. So once T1 is turned off, the path for the current is going to be somewhat like this. This is IS. So I'm going to show mainly the devices involved. So let us say this is T3. From T3, if you look at it, C1 is the capacitor, which is having plus here and minus here. So this is C1. Whereas C3 and C5, both of them come in series because T5 is not conducting. So I can draw it as though C3 and C5, both of them are coming in series. So these two are coming in series, and this end is now connected to D1. So this is connected to D1. Now, from D1, it is going to go into A phase. So this is going through ZA, and the rest of the path where it is returning, that is ZC and D2 and all, that is not going to change at all. So that is going to go through D2 and T2. So that will remain the same way. So this is D2, and we are going to have from this, we are going to have T2, and then it is going to return back to the DC source. So this is the way the current path is going to be. Okay. So once T1 is turned off, this is going to be the path. Now, because IS is flowing this way, slowly this plate is going to turn positive and this plate is going to turn negative. And we have definitely a D3 connected here, not at this point. D3 is going to be connected at this point. But that D3 will be reverse biased because of this capacitance charge being negative here. So the anode is going to be on the negative side and cathode is going to be on the positive side. So if we call this as D3, D3 will be reverse biased. Reverse biased because of charge across C1. So as C1 is slowly becoming, positive, at what rate its charge is reversing, that depends heavily upon two factors. One is what is the value of source current itself. And the second factor is what is the value of C1 itself, the capacitor value. Both these things matter quite a lot in terms of deciding how fast the charge across C1 will reverse. So once C1 value, the charge across C1 reverses, then eventually D3 will become forward biased and D1 will get out of conduction and the current will be slowly transferred to ZB. So the current gets transferred from ZA to ZB as C1 loses its charge and subsequently charges in the reverse direction. And in the meanwhile, we are going to see that C3 charges again with plus here and minus here, which will make it ready for commutating T3 when T5 is 5. So we have to ensure that the capacitors what we choose are good enough to maintain the negative charge across T1, the outgoing device. The outgoing device will be completely undergoing recombination, and that recombination will be successful only if the capacitor charge reversal does not happen too quickly. So the design of this capacitor is of utmost importance in this particular current source inverter. And C1 will be a large value invariably to ensure that this particular thyristor remains reverse biased at least for a duration which is equal to the turn-off time of the thyristor. That is one reason why current source inverter fed drives are generally not operated at very, very high frequency. So CSI fed drives are normally operated at low frequency. And they are also operated generally with thyristors. So generally it will be for high power rated drives. So when we talk about high power rated drives, if we are looking at voltage source inverter fed drive versus current source inverter fed drive, what we are going to have first of all is this is the three-phase supply, which is 50 hertz supply. Let's say. From here, we are going to have a thyristor converter, which is going to convert this AC into DC. So we have converted that into DC here. Now we are going to have an inductance here, which is trying to convert this voltage source into a current source. Now from here, we are going to have an auto-sequentially commutated current source inverter here. So this is the current source inverter. And this is the thyristor rectifier. And we are going to connect this to the three-phase induction motor drive here. So these are the three-phase windings of the induction motor stator. And here is going to be the squirrel cage. This is the rotor of the induction motor. So this is the stator. Now, when we are making this motor work in motoring mode, then we are going to have the current flowing in this direction. This is going to again flow in this direction, and the current is flowing in this direction. These are the current flow direction as far as the motor is concerned. Now, if it has to work as a regenerative braking device, in that particular case, what we are going to do is omega S will be made less than omega R for braking, regenerative braking. Under that condition, this CSI now will start working as a rectifier during braking. And this rectifier will be fired at a firing angle greater than 90. So this will work as an inverter. So what will happen is, normally we are going to see when it is working as originally it was working as a rectifier initially, we would have had plus here and minus here, and we would have called this as VD1 maybe. And we would have had here also plus here and minus here, and we would have called this as VD2. But when it is working in braking mode, alpha has become greater than 90, because of which we are going to have this side as plus. Let me write this in blue itself again. I don't want to confuse you. So let me write this is plus and this is minus for braking mode. So this is going to be corresponding to braking mode. And this would also have changed its polarity. This would be plus and this would be minus, again during braking mode. Previously, the current was flowing in this direction. Even now, the current will flow in this direction only. Only thing is, during motoring from left side, it was flowing to the right side. So motoring mode, it was flowing from VD1 to VD2. That is what was happening. Whereas generating mode or braking mode, the current direction does not change. Only the voltage polarities change. So that can be easily done in a thyristor converter by adjusting the firing angle of the converter without any difficulty. So under this condition, from VD2 to VD1, the current is going to flow. So the stored energy, kinetic energy in the rotating parts of the machine will be converted into electricity. And this CSI will now start working as a rectifier, and that will feed back the energy through this converter number 1, which was originally working as a rectifier, that will start working as an inverter and line commutated inverter mode, and it will be feeding back the energy to the three-phase side. So let me call this as converter 1, and this is the CSI. Now the CSI starts working as a rectifier and converter 1 starts working as a line commutated inverter, and braking automatically takes place. So in large capacity drive, the braking energy, we don't want to lose out on the energy that can be recovered from braking. So CSI fed drives are inherently suited for large capacity motor applications where braking can be incorporated, and it is very, very easy to change the firing angle from less than 90 to greater than 90 and vice versa. So we would be able to recover the regenerated energy very easily. Whereas if you look at the VSI fed drive, what we are going to have invariably is a diode rectifier. Even if you use a thyristor rectifier in the front end, let us say this is the front end rectifier and this is the three-phase supply. And we are going to have a capacitor which is making the voltage steady or without any oscillations. And here we are going to have the inverter. So VSI invariably will be indicated by some IGBT and diode together. So this is our VSI. Now from here, this is connected to VSI and VSI's output is going to the induction motor. Now here is the rotor of the induction motor. Now, if we are looking at again regenerative braking mode, we have to make omega S less than omega R. That is perfectly fine. That can be done. That's not a problem. So we have diodes here. These diodes will be able to rectify the AC that is coming out of the machine. That is also not a problem. So we would be able to take it to the other side. But because it's working as a rectifier, we will have plus here and we will have minus here. There is no doubt. The voltage polarity cannot be changed in the case of voltage source inverter fed induction motor drive, and the current cannot be reversed if we are using either thyristor or diode. The current cannot be reversed. And voltage cannot be reversed because of the presence of capacitor. So regeneration will not be possible in the case of a VSI fed drive unless we replace the front end converter, what is available here. If I call this as converter 1, which is the front end converter, the front end converter has to be replaced by, again, a fully controlled converter, somewhat like this. So the front end converter or converter 1, what we are talking about, this converter 1 will prevent the voltage reversal as well as current reversal. If it is a thyristor converter or a diode converter, the diode converter anyway will not allow either voltage reversal or current reversal. But thyristor converter would have allowed voltage reversal, but the capacitor is not going to allow for voltage reversal. So regenerative braking is not inherently implementable in the case of a VSI fed drive because of these constraints. Whereas current source inverter fed drive is inherently suitable for regenerative braking being implemented with ease. So in general, the current source inverter fed motor drives are used extensively in large capacity drives because in most of them we will be using thyristors, and thyristors are slow, but they are meant for high capacity. And the regenerative braking is implementable very easily because current need not be reversed at all. Voltage can be reversed right away. So all those things make current source inverter fed induction motor drive easily implementable in large capacity applications. So in general, voltage source inverter fed induction motor drives are used in small capacity applications, whereas current source inverter fed induction motor drives are utilized in large capacity applications. We will be looking at how an induction motor performs when harmonic rich currents are fed to it in the next lecture class.